Okay, so our goal now is to find out everything we can about an equation without actually graphing it, and then our next step next week will be to graph it. So what we want to do is we want to be able to look at an equation, know about all of the asymptotes, all of the intercepts, and if the equation has a hole. And you may or may not have heard of a hole before, but kind of like that graph I showed you on last week's, I'm going to scroll back up to it, that has a hole in a line. They're not always in a line, they could be anywhere, but like this, it just has one point missing from the graph that you normally draw. So that's what a hole is. So some of these things you've done or you've had experience with, just maybe you didn't call it this or look for it in this way. And then some of them you haven't, and we're going to go through them here. So we have this whole list. Okay, asymptotes, there's 3 of them: vertical, horizontal, and oblique. Holes, you may not have seen before, and then there's 2 types of intercepts, X-intercepts or Y-intercepts. We're hoping that if you can find all this information out through the algebra, that we can sketch a graph without actually plugging in points, because the graphs of these are very difficult shapes to determine. So I'm going to use these 2 examples throughout the notes, so if you want to take a minute to write them down. That way when we list over here how to find holes and how to find asymptotes, since we don't actually get to have the in-class experience, you at least have a couple of different ways that you've seen them. So the first piece of advice I'm going to give you is that we want to see the equation in its most simplified form if possible. So what that means is if the equation hasn't been factored, you do want to see it in its factored form. So that's what I'm going to look for first. So in example 1 here, I notice that the numerator of this equation has a greatest common factor of 2. So I'm going to factor out the 2. And then if I go to factor x squared plus 3x minus 4, I should get x plus 4 and x minus 1. If you use the diamond and those steps to factor, you should pause the video for a minute, go through your factoring steps and make sure you're getting them correct, because factoring is going to be extremely important to you in these problems. I'm also going to factor the x squared plus 9x plus 20, and that should factor as x plus 4 times x plus 5. And again, pause the video if you want to go through the factoring steps to see what happened there. Notice that they have a common factor that we can cancel out in this problem, and that gives us a simpler version of this equation. And I'm just going to keep that like that for right now. Okay. I'm going to go look for the same types of things in example 2. So in example 2, if I factor the x squared minus 4, I would get x minus 2 and x plus 2. And in the denominator, I have x plus 3. Here, nothing cancels. Okay, so when you look at an equation and you're about to determine the list of asymptotes, intercepts, and holes, this complete list, what you'll first want to do is see if there's anything that cancels. And this is why. I'm first going to focus on a hole. Okay, a hole has another name. You might find it a little bit complicated. It's called a removable discontinuity. It basically means what you saw right here, that there was a factor that was removed from the equation. That's why they call it a removable discontinuity. Okay? And here's the reason why. When you guys reduce a fraction, if this said 4 over 8 and you reduced it to 1/2, we say that those fractions have the same value or are worth the same thing. And in this number sense, 4 over 8 is exactly the same as 1/2. So when we cancel out x plus 4, we're saying what we had before, this original function, is the same as what we have down here. This is correct except for one complicated situation because of the variables. So this x plus 4 is a little bit trickier than just having a number. This x plus 4 could be made equal to 0 if x was equal to -4. You might think that that's not important, but here's the reason why it's important. If I plug in this x value of -4 into the very original equation, so if I plug in -4, I make all the x's a -4, I do all the arithmetic in the numerator and in the denominator correctly, what I end up getting says 0 over 0, okay? That is a crazy mathematical expression because you could say that 0 divided by 0 is 0, but it could also be 1 or 2 or 3. It has infinitely many values. It doesn't have one defined value. Now you said this new equation down here is the same thing because we just canceled out a common factor, but watch what happens when I plug -4 into this expression. If I plug -4 in here, I get 2 times -5, which is -10, over -4 plus 5, which is 1, and I get -10. But these are supposed to be the exact same thing. So here's the deal. They are the exact same thing, except for at this one spot where you canceled something out. So this is how you find a hole. So let's go to our chart where it talks about finding a hole. It tells you the other name here, and I tried to put some notes in here for you. This means that the factor can be removed or canceled from the equation. So how do you find a hole? When a factor cancels, then you set the factor equal to 0 and solve for x. So in our example, that x plus 4 had canceled out, so we set it equal to 0, and then we got x is -4. And then you plug in to the new equation to get y. So like we did here, when we plugged -4 into the new equation, we had done this arithmetic and gotten -10. -10 is the one answer that I can't really get. So for y. So this means that our hole is at the point -4 for x and -10 for y. And you would literally go to the graph and at the point -4 and -10, you would plot an open point, meaning it's going to look like the graph goes through this point, but it's really going to skip over this one spot. Okay, so we always want to look for the holes first. So start with this first. If nothing cancels, then you just say that you have no holes. So when we look at this equation here, we have none. So I'm going to make a little list for us in a different color so it doesn't get too confusing. So for us in this graph, we had a hole at -4, -10. And in this graph, our holes would be none because there was no factor that canceled out, so there's not anything weird like that that's going to happen. So the next thing we want to do is we want to go through our asymptotes. So notice there are 3 different types of asymptotes by name. There's a vertical asymptote, a horizontal asymptote, and an oblique asymptote. Notice that the horizontal asymptote and the oblique asymptote mean the same thing. Okay, that means you don't have both of these. You have one or the other. A horizontal asymptote means that you have horizontal ends on your graph, and the oblique asymptote means that you have ends that go towards -infinity or positive infinity. Okay, so referring to the previous notes, what I mean by that is when we looked at all these, this has horizontal asymptote because it landed at a certain number. This has horizontal asymptotes because it landed at a certain number. This one did not have a horizontal asymptote because all of the ends went towards infinity or -infinity. So that's why you saw in the previous notes, in this conclusion chart, that this is when we do not have a horizontal asymptote. Okay? So we can tell this, remember, by looking at the equation. Okay? So I'm going to make a little list for each of these. We're going to talk about horizontal asymptote, oblique asymptote right now. Horizontal asymptote or oblique asymptote. Now you only have one or the other. So one of these is going to say none, and one of them is going to have an equation. For the first graph, or for the first example, right here, example 1, notice the degree in the numerator, and you can see it at the beginning or in the simplified version, is the same. Okay, so go to your conclusions from before. When they have equal degree in numerator and denominator, then they do have a horizontal asymptote. It's at y equals a number, and this number is found by using these lead coefficients. So if you distributed this 2, this x would have a 2 in front of it in the numerator and a 1 in the denominator. And so that means the horizontal asymptote for this function is y equals 2 over 1, which we would normally write as y equals 2. And that means it does not have an oblique asymptote. Because the ends are horizontal, they can't go to infinity and negative infinity. Okay. When we look at the second example, the degree in the numerator is higher than the degree in the denominator. That's this situation here, and that is the situation where we do not have a horizontal asymptote. So here we would write no horizontal asymptote. That means we're going to find an oblique asymptote. So let's go back to our chart and kind of read about how to do that. So horizontal asymptote, you want to just see your conclusions above. We discussed that in the last notes very in detail, and that's how we've been figuring out if there is a horizontal asymptote. For the oblique asymptote, it still is for the ends, but they're going towards infinity or negative infinity. So you basically want them to be able to follow a line to know how fast they're going up or down. And so what we want to remember here is that a rational function is written like a fraction, and a fraction is really a division problem. So when you have to find an oblique asymptote, you're going to use division. Okay, so I'm going to go back to the problem we're working on to find an oblique asymptote. And I want to actually do this division in this problem. So it's actually easier for me to use the original way the problem was written. So I want to do x squared minus 4, but remember we need a 0 placeholder when it doesn't have a placeholder like that. And I want to divide it by x plus 3. So you guys are going to go through the division process we talked about a couple weeks ago. So what we're going to do is we're going to find out which number times x makes exactly x squared, and that would be x. And that x is now going to multiply this entire group of x plus 3. So it's going to distribute to each of these terms. So x times x will be x squared, x times 3 will be 3x. And then remember, those are being subtracted from the previous quantity, which can be turned into addition if we distribute that negative to each of the terms. So those cancel out. We'd get negative 3x here and drop down the next term. And now we'd start the division problem over, asking ourselves, what do we want to multiply times x to get negative 3x? The answer to that question is negative 3. And that negative 3 now distributes to each of the terms in here. So negative 3 times x will make negative 3x. Negative 3 times 3 will make negative 9. And again, we're subtracting this entire quantity, which can be viewed as addition if we distribute the negative sign. And then we have a remainder of 5. So the actual answer to the division problem is x plus 3 plus this remainder. But when we go to write the oblique asymptote, we actually do not include the remainder. Because when we're trying to find end behavior, we're talking about x getting really big, like way out to the right side. And if x is really big, think about like if it's 1,000,000 or something. If you had 5 over 1,000,000, this number is so teeny, teeny, tiny that it's almost like nothing. It's almost rounded to 0. So since we're just trying to get a guideline of what our graph should follow, we ignore that portion since it's such a small amount, and we just use this part here. Okay, so again, look back at your chart. In the oblique asymptotes, you're going to use division, but you're not going to use the remainder portion. And so you're going to get y equals, and you're going to get a little equation here rather than a number, because you're following a line towards infinity and negative infinity rather than staying horizontal at one specific value. Okay, so that's how we deal with our horizontal and oblique asymptotes. It's one or the other, and we can tell by looking at the equation. If it's a horizontal asymptote, we just have to have these conclusions memorized to know how to do it. If it's an oblique asymptote, we have to do division and a little more work to figure it out. Okay. The last type of asymptote listed here is a vertical asymptote. So you might be thinking that we didn't really discuss how to find a vertical asymptote. That's because you guys kind of already know. You just might not think about it in this way. So a vertical asymptote is where the function is undefined. Okay, and again, it also has another name, a non-removal discontinuity, because like a whole, this is going to break our graph apart, but you don't see it get canceled out of the equation. So if this is where the graph is undefined and you have a fraction, so a fraction has something in the numerator over something in the denominator, if you're looking for the places where the fraction is undefined, you're looking for the places where the denominator ends up being 0. That's when we get undefined values. So to find our vertical asymptote, we're going to set the denominator equal to 0 and then solve for x. So our vertical asymptote should look like x equals, and you might have 1, you might have more than 1, it just depends on the denominator. So let's look at that for each of our examples over here. For our vertical asymptote in example 1, we've already dealt with the whole, so we don't want to look at this beginning version. This already canceled out. We want to look at this new version here. The denominator of this function is just x plus 5. If I set x plus 5 equal to 0 and solve for x, I get that x is equal to negative 5. That's my vertical asymptote. Okay. In my second example, x plus 3 is my denominator. If I set x plus 3 equal to 5 or equal to 0, I would get x equals negative 3, and I have one vertical asymptote there. Just a side note, if you had a function where you had more things in the denominator, when you set that denominator equal to 0, you would have multiple factors to set equal to 0, and that would give you more than one answer for your vertical asymptote. So if I looked at a problem like this, it would have 2 vertical asymptotes at x equals 2 and negative 3. So again, for our vertical asymptotes, your note is that you want to set the denominator equal to 0 and then solve for x to see where those are. The last things on here, again, you've found with each thing that we've studied. So you do know how to do this. It just might be a little more complicated here, is finding the intercepts, so the x-intercept and the y-intercept. So for the x-intercept, you set y equal to 0, and then you solve for x, and these are points that your graph should cross through, x, 0. Maybe you have more than one, maybe not. Okay. For your y-intercept, you set x equal to 0, and you solve for y, and then you get answers where you have 0, y. You will only have one y-intercept because these are functions. They pass the vertical line test, so you won't see something where you get 2 different values for that x. So let's go find these, and then we'll be done with this lesson. So for this first example, if I want to find my x-intercept, again, we're using the more simplified version of the equation. I'm going to take the equation, and I'm going to set y equal to 0. So that looks like this. And here's where those previous lessons come in that reminded you how to solve equations. This equation's tricky to solve because the x plus 5 in the denominator, but you saw earlier in this unit that if we just multiply by that factor, we can cancel it out. We'll multiply that by that on the other side as well, and 0 times anything ends up being 0. So then we have this much simpler equation to solve. And so we would divide both sides by 2 at this point. We'd have 0 equals x minus 1, so x is equal to 1. And remember what you were looking for. You were looking for x-intercepts. This is a point. We got an x value of 1. Okay. We're also going to try it for our second function here. So if we are looking for our x-intercept, we take this equation and we set y equal to 0. And again, you have this rational function. This situation is going to keep occurring every time because of the type of function we're working with. So you want to multiply by that factor in the denominator. And again, 0 times anything is 0. And in this case, we have two factors that we can set equal to 0. And we would get 2x values. So here we have two x-intercepts. Our graph is going to go through 2, 0 and -2, 0. And then lastly, for each of these, we want to find the y-intercept. So to find the y-intercept, remember you're taking the most simplified version of the equation, but this time you're plugging in 0 for x. And so when we do this here in this equation, it'd be 2 times -1/5, which is -2/5. So that's my y-intercept. And remember, that's a point where x is 0 and y is -2/5. And then I'm going to do the same thing for the second example. So again, I'm plugging 0 in. It technically doesn't matter which form you use. So if you find one form more convenient than another at a certain point, you can do that. So this gives me -2 times +2/3, which is -4/3. So my y-intercept here is 0, -4/3. And just again, a side note on something that could happen. Let's say that you were solving for an x-intercept for something like this. And so you set y equal to 0. And you went to solve this equation. So you'd get 0 equals 2. This is not a valid solution. There's no x left in the equation to solve for, and 0 equals 2 doesn't make sense. So this equation has no solution, and then you have to remember, what were you looking for? You were looking for x-intercepts, and the equation that you set up to do that had no solution. That means you don't have any x-intercepts. It wasn't possible to find them. So don't be afraid of getting that none answer at any point in time for anything in your list. So again, the emphasis here is to be really good at looking at an equation and finding this entire list of information, all asymptotes, holes, and intercepts, because our next week we're going to take this information, plot them all on a graph, and see if we can sketch what these crazy graphs look like using this information to guide us.